So, welcome to the second part of our mini course on computational methods in continuum mechanics. And today we'll be talking primarily about finite element method, talking about its theory and do some practical things with it also. Okay, so outline. First, as I mentioned previously, I will have to give a very short introduction into variational formulations, because that's what we are going to need in finite element method. But I try to make it as simple as possible. Then we will discuss about the finite element method itself, what are the ideas, basic ideas behind it. In more details about one specific case for heat conduction, probably one of the problems that we considered on the previous lecture. And we will solve an example, code this method for a relatively simple two-dimensional problem. And we will discuss the second part of the assignment, which forms the assignment together with the first part that I gave you previously. Okay. So let's start with something extremely simple. The simplest thing in mechanics is a mass spring system. You cannot imagine of anything more simple, but already I can show you the idea of variational formulation using this simplest possible example. So let's imagine we have a mass spring system in a gravity field, so it's fixed, the top end of the spring is fixed, and we have some mass on the bottom end, and there is gravity acting, and we are interested in displacement. For sure, there is no problem for you to tell me the answer to solve this problem. Okay, so it's you write down the balance equation. So gravity force must be equal to the elastic force produced by the spring, and from there the latter one depends on displacement, and from here we can find displacement. Okay, as simple as that. And that is called strong to direct formulation. Well, direct is kind of obvious. We write down balance equation. Strong is because in more general case, which we will be talking about later, in continuum mechanics there are derivatives. And this type of formulation, the one we considered, it requires higher order derivatives than in comparison to the second one that I'm about to talk right now. So another formulation is a variational or weak formulation. Variational because it's expressed using ideas of calculus of variations, and weak because it has relaxed requirements to the function. We will see later that there are derivatives of lower order than in a strong or differential formulation. So in this particular case, you're pretty much aware that we can solve this problem using potential energy minimum principle. Okay, so we write down potential energy, which consists of a term related to elastic energy of the spring and potential energy of this gravity force. And then we require that it has minimum. We calculate derivative, and we get exactly the same result. Of course, what else could we get? What does it has to do with variational formulation? So it does not seem to have anything, because it was for a 1 degree of freedom problem. We have only one unknown displacement, so there is no room for any continuous functions for any variations. But the idea is still the same, but in more general case, if we had some continuous problem with a displacement as a function of some coordinates, x coordinate vector, position vector, and then we still would be able to formulate potential energy, which would depend on that displacement field. And in this case, it's u is not just a scalar value, it's a function. It's how displacements are distributed across our domain. And then we still are able to calculate potential energy for a certain deformed shape. You probably have some experience in that. And we call that functional, because it's a rule how we assign some scalar value, potential energy, to a function. A function is a dependence of displacements on coordinates distribution, displacement field. And in that field, in that case, it will be a little bit different, because it's not a function, it's a functional. And I use square brackets to emphasize the difference. It's one of convenient ways to do that. So whenever you see in my writing here, whenever you see square brackets, that means I'm talking about a functional. And when you see parentheses, then I'm talking about a function. But still, the idea would be the same. We will be seeking for a stationary point of this functional, for a function u, function of coordinates, that provides stationary value to my functional. It can be minimum or it can be maximum, but in general case it's not necessary. It could be also a saddle point. So we are talking about some stationary point, so where the first variation of functional is equal to 0. I will show a little bit more rigorous definition of that on the next slide. And then from there we find our displacement. So basically the idea is the same as minimum potential energy principle, but if you express it in continuum mechanics, then you have to deal with functionals, because potential energy depends not on displacement at some particular point, but on distribution of displacements all over in our system. And then we have to deal with variations. Okay, so very small piece of rigorous definition. So if we have, in general case, we have some kind of functional. So functional is a rule how we assign a scalar value to a function. So it takes, as input, it takes in displacement field. For instance, it doesn't have to be necessarily displacement field. It can be something as a function of time as well, or anything else. But what we will be dealing with is a displacement field, and we will be also talking about temperature field, but basically you probably can grasp the idea. So that's a functional. And if we calculate this limit, so we add something to our argument, to this function, we add something, a new function. It's usually, this notation is usually used, delta u, which means that it's kind of variation of our function, but rigorously speaking is just another function. It's also called sometimes test function, multiplied by some factor, some coefficient, which we will be consider approaching to 0 later. And we calculate difference about this, the value of this functional for this modified function, and the value of this functional for the original function, divided by this factor which was used here. And as it approaches 0, then what we get, this limit, is called first variation. So it's, you can see that it's basically very similar to what we call a derivative or differential of a function, but in terms of functionals. So when we switch to the world of functionals, we need to adjust a little bit our definitions, but this calculus of variations has a lot of similarities with differential calculus. So you will be able to use actually some equations that you already know from differential calculus, apply it in calculus of variations. Please do that with some, do that carefully. There might be some reservations, but in general, since the definition is quite similar, so rules are also quite similar. There is some specifics in calculus of variations. I'm not going to go into it right now, so I'm just only going to describe it on this kind of surface level that is necessary for us to understand during this lecture for talking about the finite element method. Okay, so how does it look? Comprehensible? Okay, so if we are done with this definition, then this general statement of a variational principle looks like that. So we require that this first variation of the functional is equal to 0, but contrary to differential calculus, we need to put here something else. Because in differential calculus, you just say that my derivatives, if I'm looking for an extremum point, then I just say that my derivative must be equal to 0 at that point. In this case, it's a little bit different because we still have these functions here and test functions, and there might be different test function. So the point of this statement is that this quantity, which in general case depends on this test function, this delta which I use. Nobody guarantees me in general case that if I use different test function, I will still end up with the same limit. It's not guaranteed in general. But the statement of variational principle is that we are looking for a function u, so that for any test function here, put it into this first variation, it will be equal to 0. So this limit will be equal to 0 for any test function. So no matter how I change my displacement field, if I change it slightly, this functional does not change to the extent of first order terms. That's basically the idea on hands. So it's similar to derivatives, but a little bit more statements here. So I use this quantum for any. So for any test function delta u, this first variation must be equal to 0. That's what I'm looking for. I'm looking for a displacement or an unknown function u that ensures this statement. If I find this kind of function, then it means that it's, well, mathematically it means literally what is written, nothing more. But in application to mechanics, usually it means if I use something meaningful as a functional, let's say potential energy, or something else. There are different variational principles in mechanics. So then that usually means that this function that satisfies this statement is exactly the function that I've been looking for. It's exactly the same function that satisfies also differential formulations. I will not be proving that for any cases right now, but you can find such proofs in books. By the way, I forgot to mention this first slide that I introduced here as a company to the book by, but I introduced also here one of the classical books about finite element methods by Zienkiewicz. So that's actually one of my favorite ones. So if you want to go into more details about finite element methods, I highly recommend this book. About variational principles, you can find something in Bata as well, but of course there are also plenty of other books about calculus of variations. And variational principles in mechanics are also covered in many books. Okay, so we're here. So that's basically how variational principles look like, and what's inside. A little bit of this inside mechanics. Okay, let's try to consider an example. how does that apply to the problems that we considered previously? Let's say we are looking for a solution of this two-dimensional elasticity problem. Oh, sorry, not elasticity, heat conduction problem. It's a little bit simpler than elasticity because we have one degree of freedom at each point. We have only one unknown quantity, it's scalar quantity temperature. In elasticity, it's usually a two-dimensional or three-dimensional vector, displacement vector. Of course, you can also formulate a one-dimensional elasticity problem, and I will actually ask you to do that in your home assignment. Okay, so this is the problem you are already familiar with from your previous, from our previous discussion, and we are looking for the distribution of temperature. Temperature as a function of two coordinates x and y. And for this type of problem, for heat conduction problem, the functional for variational statement will look like that. So I'm not proving that, but you can find this proof in the book by Bate, for instance. There are proofs for several variational statements, including this heat conduction problem. This type of heat conduction problem. Not exactly with these boundary conditions, that's what I just came up with for our lecture to test the approach. But why the function looks like that, I will refer you to Bate or something else if you prefer. Okay, so there is an integral across the area of this domain of this quantity. K is heat conductivity, and those are partial derivatives, and that's this first term. The second term is about boundary conditions. It's about heat flux prescribed on the boundaries. So I formulated it in general way here, like integral over entire boundary, and there is some specified value of heat flux. Okay, I will be using two particular values, Q sub 0 and Q sub B, for my two boundaries with non-homogeneous boundary conditions of this type, but this is general formulation. So the boundary conditions could be different, it would still be the same. So what does the variational principle say in this case? So this is the statement of variational principle in this red box. So first variation of this functional must be equal to 0 for any variation of temperature or for any test function. Yeah, we already discussed this step. But here it comes with additional restriction. So in this problem, we also, aside of heat flux type boundary conditions, we also have prescribed temperature on one boundary. And we need to specify that boundary condition explicitly in addition to this general statement of variational principle. And it can be proven. Again, you can find that proof in Bate, for instance, for a similar problem. It's not exactly for this type of boundary condition, but in general for this type of problem. That if you find a function t, a field t, that satisfies this statement in the box, this very field t will also satisfy this set of equations. So there is a mathematical yield. So this one in the box yields this set of equations. And this in the right hand side of our slide, this is exactly the statement of variational strong formulation of our heat conduction problem. We discussed it previously. So it goes also in the opposite direction. So those are equivalent mathematically. And I wanted to emphasize you that you see that there is a fundamental difference in how we treat different types of boundary conditions here. boundary conditions when we prescribe heat flux. We mentioned last time that they are called natural boundary conditions, and they are inside the functional. If we use variational statement, those boundary conditions must be incorporated into the functional. Another type of boundary conditions prescribe displacements. Oh, sorry, not displacement, temperatures in this case. And this is what we call essential boundary conditions. And we need to manually prescribe them in addition to this general statement that first variation of the functional must be equal to 0. Okay, so it makes sense to keep this difference in mind when you are using finite element method, even if you are using commercial software. If you are not coding it yourself, you still better keep this difference in mind, because it will be in a different way how you prescribe, for instance, what is the default boundary condition. If I don't say anything explicitly in a commercial code, for instance, about boundary condition, what will the code assume? Well, from this formulation you can also already see that it will assume something 0, but what 0? Temperature 0 or heat flux? Okay, since there is this variational principle inside this functional, so it will form this vector, and if I am not prescribing anything, it forms the 0 values here. So natural default boundary conditions would be, in this problem, natural boundary conditions with 0 heat flux. So this insulation on this bottom line here means 0 heat flux across that boundary, and that will be kind of default boundary conditions if you're using commercial codes based on this variational formulation. Okay, but it will be more clear when we do it ourselves with coding. Okay, so can we go further to the finite element method? So that's very brief introduction. I tried to make it as brief as possible about variational principles in continuum mechanics. So I just give you this functional, but basically if you are dealing with a standard type of problem, you already know this functional. It's not a unique statement. It's possible to think of other types of functionals that would also lead to variational principles equivalent to the same strong formulation. Just keep that in mind. At least it's very relevant to mechanics when we are talking about elasticity problems. Then there are different variational principles used. Okay, so now we are moving to the main topic of our today's discussion, the finite element method. So judging from the name finite element methods, you can assume that there must be some finite elements. And basically it's a good name for the method because it gives you a pretty good idea about what is it about. And it is about discretization of the domain. So you split your computational domain, the area where you want to find something, some field, displacement, temperature, electric potential, whatever. You split it into some relatively small volumes. And those volumes are called finite elements, and they have shared boundary, and they share what we call nodes. In this example, I draw them on intersection of the boundaries, but there might be different nodes there. We will mention that very soon. Okay, so I put down kind of formal definition here that you can refer to. The domain is approximated by a finite number of non-intersecting subregions, finite elements, which have common nodal points, nodes. So that's kind of geometrical vision of the finite element method. Of course, it doesn't help me much to solve differential equations or to solve a variational statement. It's just how we treat the domain. But it has to do a lot with mathematical calculation of unknown quantities as well. But before we dig into math, and we will have to dig a little bit deep into it, so it might become a little bit overwhelming. Hopefully not, but sometimes it is when people deal with it first time. But before we dive into that, let's talk about easy stuff a little bit, because it's also useful to get a more general picture. So in this case, I draw this two-dimensional domain. So what kind of shape might those elements have? What is in my picture is kind of quadrilateral elements with straight boundaries. But it might be something different. Talking about straight boundaries, it might be triangle subdomains. So we can easily divide this volume or this domain into subdomains of triangular shape, keeping the same concept of that they share boundaries, they share nodes. It's possible, why not? Or they might be a little bit more irregular form, still quadrilateral, but it's not necessary that they are of this shape as in my picture. Not necessarily rectangular ones, I mean. But they may also have nonlinear boundaries. We are not limited to elements with linear boundaries, of course. They might be boundaries described with second-order equations, which is actually pretty often used. So there might be something more complicated, like you could use some third-order splines or whatever, any power of terms. But in practice, the majority of cases, majority of situations, what is used is linear or quadratic finite elements. That refers usually to how the known function is interpolated, and we will talk about that very soon, but it also refers to their shape. So their shape might be with linear edges, and it might be with quadratic edges. Might be something else, but those are two the most commonly used. So this is how it would look for a triangle element with nonlinear boundaries, and this is how it would look for a quadrilateral element with nonlinear boundaries. Please keep that in mind for future, for your engineering future, or whatever you decide to do in your life. If you are dealing with finite element methods, please keep in mind that you also approximate shape of your body that you are simulating. And it might be not important in many cases, but sometimes it might be very important. For instance, if you are looking into contact interaction between this outer boundary of my domain and some other body, then you might see some very peculiar results if you use linear approximation here, like because you will have some kind of angles there on your surface. Okay, just keep that in mind that you are approximated the geometry. Not only what's happening inside the distribution of the function that we are looking for, but also the geometry. Okay, in more general case, this was our example was about two-dimensional situation, but it might be kind of easier if we are dealing with one-dimensional objects, something like a bar, for instance, that we don't want that has one-dimensional much larger than others, and we are not interested very much in what's happening inside, and we can formulate equations like you did for beams and rods and this type of structures, and we can use finite element methods as well, and it will result in what we call one-dimensional element. It can be still placed in three-dimensional, so you can consider a beam in a three-dimensional setting. So it might be a little bit confusing about these dimensions, what exactly we are meaning by that, but In this case, I'm talking about shape of finite elements. So one-dimensional finite elements, two-dimensional finite elements, and three-dimensional. Of course, in three-dimensional, there is a little bit more of options on the basis of triangular and rectangular, what you can build. It's not only hexahedral type of element and tetrahedral, but also you can build some pyramids which have a quadrilateral shape in the basement, and all other faces are triangular, or it might be a prismatic element. And actually, when you are mixing different type of elements in your domain, and in a real engineering world, it's pretty common situation that you are unable to divide your domain into only hexahedral elements, for instance, because it has complicated shape and you don't have a good enough algorithm how to fit hexahedral elements into it, how to approximate it entirely with hexahedral elements only. But you still might want to use them in some parts because they have certain advantages in comparison to tetrahedral elements. And to connect one to them, you can see that they are not directly compatible. We mentioned in the beginning that finite elements must share nodes, and it wasn't written there, but it's assumed that they must have also shared boundaries, shared faces. And they're not compatible. This one only has triangular faces, and this one only has rectangular faces. But we could make a transition from one to another using pyramid elements, which have both triangular and quadrilateral faces. Okay, so there is a lot could be said about how to make this division into subdomains. In engineering practice, it's usually called the meshing process. So this is a finite element mesh, and how to make this mesh for our domain. Usually it's called to mesh the domain, and there are algorithms and strategies, so there are a lot of things, but I just want you to be aware of how it can be in real world. Okay, now a little bit more into details. Of course, this geometrical approximation is of course not everything about finite element method. It doesn't help me itself to solve a mathematical problem. So the core of finite element method, or second part of this core, is interpolation of the unknown function within the element. Let's say we have this type of element, quadrilateral element, but not rectangular one. And let's say each of its nodes, I've numbered them, 1, 2, 3, 4. And let's say each node is described, position of each node is described by a pair of coordinates, x and y, so with corresponding indices. And usually what is done in finite element method, we make a transition to local. We introduce local coordinates that have meaning within the element only. It makes things much more easier later. So let's introduce some kind of local coordinates within this element. The coordinates which have 1 or -1 values at each node. So this is how it would look like, this representation of local coordinates, psi and eta. And for instance, this first node, which is the same node, it's another representation in local coordinates. In local coordinates, it has its position is described by a pair of -1, -1. The second one, 1, -1, and so on. Okay, I assume that you are in general aware of this type of transformation, like moving from one coordinate system to another, and this transition can be described by a Jacobian matrix consisting of partial derivatives of one coordinates with coordinates from one set with respect to coordinates from another set. Oh, that describes the relationship between those two. If I know exactly this shape, I can of course write explicitly those functions, how coordinates x and y can be calculated knowing coordinates xi and eta. But that would be for this particular shape, if I want to put it on the slide, so that's why I don't do that. Okay, that's what we will be using to describe a position inside the element. So I will be using this set of local coordinates to describe what's happening inside my element. It doesn't mean that I'm only dealing with rectangular elements, because knowing these transition rules I can do with any elements of any shape. And it's not so complicated to incorporate that into your code. In our example, we will be dealing with rectangular elements for simplicity, but in general it's not a big problem. Okay, so now the interpolation itself. So let's assume that we know values of temperature. We are looking how to find a solution for a heat conduction problem. So I'm talking about temperature. My known function is temperature field. And let's assume for the moment that I know values of temperature at positions of my nodes, here, or in other words here in these coordinates. And I call them T1, T2, T3, and T4. And I will be using this linear interpolation. So this expression here tells me how I can calculate temperature at any internal point, interior point of my element, using these four values and using the assumption that it varies linearly with respect to coordinates. So I don't know anything about real temperatures inside of this element. I assume that I only know those values at nodes, at corner points in our case, and I assume this linear interpolation. So inside my element, I assume that its temperature is changing linearly. So that has to do with this division, geometrical division. So we split our computational domain into subregions, and we make some assumption that within each subregion the known quantity is changing according to some predefined law. In this case, it's linear interpolation. So I make an assumption that within each finite element, temperature is changing linearly with respect to coordinates. That is how it looks like in local coordinates. It's enough complicated even for this very simple case. It might look a little bit cumbersome, but that you get the idea why we are dealing with local coordinates. Because if I try to explain the same simple idea for general shape of this quadrilateral element with linear boundaries and in a global coordinate framework, it would be much worse. Okay, so no point actually in this case in doing that. Okay, this what I have here in front of these values of temperature at my nodes, or nodal temperatures, I will be calling them this way, T1, T2, T3, and T4. In front of them, I have some functions of local coordinates. And there are four of them. They are a little bit different. So I will be denoting them N1, N2, N3, and N4 according to the number of corresponding node in front of temperature related to which it appears in my interpolation function. And they are called shape functions. So when you are dealing with finite element methods, basically you are always be talking about some shape functions. So shape functions is about which interpolation of unknown quantity you assume inside each of your finite element volumes. It's clearly that since we are talking about some assumption that we are assuming something that it changes according to a certain way, in this case linearly, clearly the smaller are the dimensions of my finite elements, the better it can be, the closer it can be to reality. So that's why in general case you would be interested to make a finer mesh of consisting of smaller elements. So shape functions. And this the same equation that I have here in the top part of my slide, I can express using this summation notation. Okay, so it's a sum of n sub y multiplied by t sub y. T sub y means temperature at node number I, and n sub y means shape function with corresponding number. So these shape functions, they are known. This is part of characteristics of my finite element approach. I assume certain type of shape functions. I know them. I can do with them anything because I know them explicitly. They are relatively simple. It will be a little bit more complicated if you wanted to use quadratic approximation. But the idea is still the same. So I'm using linear interpolation in this example. Okay, and another type of writing that I will be using is this matrix notation. So if I can compose some kind of this row type matrix out of those shape functions, I put them here. So it's a matrix, but its components depend on local coordinates. It's a shape functions matrix. And then I multiply it by this column of nodal values of temperature. So this is exactly the same, just matrix notation that is convenient in finite elements. Okay. So far clear? Okay, let's try to see how it helps us to solve this heat conduction problem using variational statement. In variational statement, we have this functional that is used for variational formulation of my heat conduction problem. And there are derivatives of my function with respect to unknown function with respect to coordinates. By the way, maybe this is a good moment to appreciate this difference with the usual approach. Maybe we could have done that a little bit earlier. Let's for a moment take a break and look into this variational statement. So variational statement says about first variation of my functional. Functional for this heat conduction problem includes only first derivatives of temperature with respect to coordinates. That is different from our direct or strong formulation that we introduced earlier, because this one includes second order derivatives. And that's one of fundamental difference between those two approaches that is important for finite element analysis or for any numerical methods actually. We do not need to calculate second derivatives when we are using variational formulation. Practically, we don't need that, so we have a little bit more relaxed requirements to our function. Okay, so let's go back to where we were. Okay, so I mentioned that I will be using this approximation of temperature within each finite element using those shape functions. And that's how we can formulate that. And finite elements, for each finite element I can calculate this functional. And I hope it's clear that this functional is an additive thing. So that means that the value of this functional for the entire domain can be calculated as a sum of values calculated for each particular domain. So that's what I put here. Okay. So we notice that we have those second derivatives. How we can calculate those derivatives if we know our interpolation? Let's calculate, they are first derivatives. They are to the second to the power 2, but they are first derivatives. So if I am using this interpolation, this one, and I want to calculate derivative, what does depend on coordinates here? Those are just values of temperature at nodes. They do not depend on anything, just scalar quantities. I cannot differentiate them. The only thing I can differentiate are those shape functions. They do depend on coordinates, as we noticed. And I can say that derivative of this temperature, so if I calculate derivative of this expression with respect to psi, it will look like that. Partial derivatives of my shape functions with respect to psi. With respect to eta, I will have those partial derivatives of shape functions with respect to eta. All right? So this is a little bit smaller, but I hope you can see it. I can calculate this quantity that is here in the box, sum of squares, using this matrix approach. So I make this matrix of two-element partial derivative of temperature with respect to psi and with respect to eta, and I multiply it or calculate a product with a column of the same quantity. This results in a sum of squares. Okay, now it's getting a little bit starting to look a little bit more complicated, but I hope you are following my story, and then it must be all clear. I really hope for that. So this column, for instance, this column is composed of partial derivatives with respect to psi and eta. Those are these derivatives. Each of them can be calculated as a product of this row type matrix of partial derivatives of shape functions and a column of unknown temperature vectors. So if I compose this matrix consisting of partial derivatives of shape functions with respect to local coordinates, first row is partial derivatives with respect to psi, second local variable, and second row is partial derivatives with respect to eta, our second local variable. And then I calculate a product of this matrix with a column of unknown vectors. I get exactly this column of partial derivatives, right? So you just substitute these here. You can see those, and this gives me this column. So this column can be expressed as a product of this matrix. I will be calling it B, matrix of gradients, because it consists of partial derivatives of shape functions with respect to coordinates, local coordinates, and we can calculate them all. We know them a priori. Once we have decided about shape functions, we can calculate this matrix. So there is nothing unknown here in this matrix. Those values, yeah, of course I don't know. In reality, I don't know them. I'm talking now as if I know them, but in reality, we will be finding them as a result of finite element solution. So this column can be calculated as a product of this matrix of gradient B times nodal temperatures, T with this superscript E, which means that it's related to a certain element E. This row type matrix here is a transpose of this column type matrix. So I can calculate it as a transpose of this product of B and TE, which really results in a product of T transpose with B transpose. Okay, so this entire thing, this product of two matrices, or in other words, this sum of partial derivatives, using our finite element approximation, we are talking about what's happening inside each element, can be calculated this way. So transpose vector of or transpose column of nodal coordinates, which is a row of nodal coordinates, in the left, just this column of nodal coordinates in the right, and inside we have this product of B transpose and B. B is this gradient matrix. I can calculate it if I know the shape functions. Okay, so at any point within our element, any interior point, I can calculate this thing that is in my functional using this expression. So my approximation, in our case it's linear approximation, but the approach is the same. My approximation of temperature within each element leads to some relatively simple equations how I can calculate our functional at each point inside the element, knowing only values of temperature at the nodes, at corner points in our case. Okay, so I only changed in this slide to this part in the bottom right angle and corner, and I am going to talk about this B matrix. So I already mentioned that it's called matrix of gradients. It's composed of partial derivatives, and for our case once we have decided about shape functions, we can calculate it. In our case, the shape functions, they were somewhere here. Where are they? So those are shape functions. This is n1, this is n2, etc. And we can definitely calculate those partial derivatives. Why not? So partial derivative of n1 with respect to xi will result in minus 1/4 times 1 minus eta, right? So that's what I did here. I calculated all those partial derivatives. I factored out this 1/4, and I have this matrix with components depending on local coordinates. In this case, it's linear because we are using linear interpolation, linear finite elements. So it may be non-linear if you're using higher order elements, of course, but you can still calculate it. This is our gradient matrix. We actually know it. Okay, so a little bit of things are left. Actually, this is the most fundamental part. If you have followed so far, then I hope you will get to the end with a clear understanding of how finite element method works. So, this is my expression for the element contribution to this functional. This is actually energy. Physically, this functional represents energy, but it doesn't matter so much for our finite element approach. Once we know that the variational principle works, then it can be something else, but it's usually actually it's energy, some kind of energy, free energy. Okay, so I substitute that here, and I have this equation. What about this right term here, this term including boundary conditions? I just substitute my interpolation here. Instead of temperature at some arbitrary point, I substitute this interpolation. And matrix of my shape functions times column of product with the column of unknown nodal values. So now what we have done actually? We have built an expression that once we know nodal temperatures at 4 nodes of our element, any element in our mesh, then we are able to directly calculate contribution of this element to this functional. Okay, there is nothing unknown except for those nodal values of temperature. And then I can calculate sum over all elements, and I will have this full functional for our problem, some value. Okay, so I will present it a little bit differently. So this first term in our element contribution to the functional, I can factor out this transpose vector of nodal temperatures and this vector of nodal temperature to the right, the first one to the left. And what's left inside is something that I can calculate. It's something that depends on matrix of gradients, which I know, gradients of shape functions, and conductivity. This is property of my medium. If it's a homogeneous medium, then this conductivity will have the same value everywhere, right? Otherwise, it may differ, and I can use different conductivity for different elements. Not a problem. So if I have a domain that consists of two materials with different conductivities, then for elements which are inside first domain, I will use one conductivity, and for elements which are inside second domain, I will use different value of conductivity. So it's not a problem to use this approach if we have non-homogeneous material. Not a problem at all, nothing changes at all, not even a small thing, just values of this conductivity that I substitute calculating these integrals. And this what's in the parentheses, except of this factor 1 or 2, is called element conductivity matrix. Okay, so I will be using this notation key with superscript E, because it relates to element, and this is bold key, this is regular key conductivity property, and this is matrix, this is bold, but it has to do with conductivity. Okay, so again I put it here again, this conductivity matrix for an element. For our particular, so I mentioned that we can calculate it as well, but there was one moment where you should be careful that all those things as we wrote them, this B matrix, for instance, they are in local coordinates. But in the end, we will have to talk about global coordinates. We will have to make this transition to global coordinates at some point. And this is a good point where you should make it. You should calculate this integral over real area of the element, and then you will have to make this transition. We will use the Jacobian matrix, of course. And in my example that I want us to do together today, we will be using rectangular elements of this type. And so this D represents aspect ratio of our elements, A and B being the dimensions of the element. And then this, we can actually calculate this integral. And this already includes the transition to global coordinates, so the Jacobian matrix, Jacobian of transformation from local to global coordinates. So there is what is inside this matrix. So in front of it, we have this conductivity property. It just because it's just conductivity of our material. And inside, we have nothing but aspect ratio. So it could be a little bit more complicated, of course, if I considered not a rectangular element, but more general shape. But let's make it, keep it as simple as possible. We still are able to solve quite interesting problems even with the rectangular elements. So you can do that by yourself to check. I just give you an answer here. That's what it results. But the idea how to get it, I hope you already see from here. Just careful calculation of the integrals. And this is actually where numerical integration is used. The numerical integration that you studied with Grzegorz 2 weeks before In real finite element analysis, it's used to calculate those integrals, those properties related to elements. It might be element conductivity in our example, it might be element stiffness matrix in case of elasticity, for instance, or something else if you are dealing with different type of problems. But in our case, I can calculate it analytically, because I'm using very simple elements, but in general case, it's calculated numerically, and those numerical methods that you considered, they can be used here, and they are used. Okay, so there is just basically one step left. How to make now this, how to formulate the variational principle to be able to find the distribution of temperature using this interpolation that we assumed. So we will eventually have to deal with global vector of nodal temperatures. So I constructed here a vector of, in this order, might be a little bit different order, and I will show you where it, how it then, what difference does it make. But here I made it its first temperature of the first element, so the subscript denotes number of node within element, and superscript denotes number of elements. So first I put 4 temperatures for the first element, then for the second element there will be less than 4 because they are connected, and they probably are connected, they probably share some nodes. So let's say they share nodes 1 and 4, and that's how it will be in our example later. And then there are two nodes related, 2 additional nodal temperatures related to second element, and then etc. So I use here temperatures at all nodes of my finite element mesh. Global vector of temperatures. This is what we are going to find as a result of finite element solution. And before that, we were dealing with element nodal temperatures. 1, 2, 3, 4. Each element has 3 nodal temperatures. And we can design some kind of matrix how to extract appropriate nodal temperatures, element level temperatures from the global level. So for this example, for instance, it will be this type of matrix. So if I use global vector of temperatures and I want to extract temperatures that relate only to the first element, these first 4 elements, I make this type of matrix. It's not square matrix. It has the number of columns is equal to this total number of nodes, the dimension of my global vector, global temperature vector. And the number of rows equals to the number of nodes of an element, of one element. So in our case, it's 4. And I put diagonals here, and everywhere, everything else, I put unity and diagonal elements here, and everything else is with 0. And if you calculate this product of these 2 matrices, this matrix and this column, you will see that it's just a column of 4 values, exactly nodal temperatures. For a different element, it will be a little bit different matrix. It will be still composed of values 1 and 0. Most of the elements will be 0. Some elements will be 1, and they actually described where nodal temperatures related to this particular element are located in this global temperature vector. So it has to do with the enumeration, how you assign numbers to your nodes and how you compose elements. We will make an example and we will see that it's relatively simple. It can be made relatively simple. But this is the idea, that for any particular element I can have this matrix which I know if I know how the mesh is constructed. It describes how are the elements connected. And then I can use this matrix to extract element nodal temperatures from the global nodal temperatures. Okay, so how can we find this global vector? This is done by solving a system of linear equations and how to get it. Okay, so what we already know how to calculate is how to calculate this element contribution to this functional. And then we can sum it over all elements. And I know how to extract element temperature from the global temperature, so I can use this extraction inside here and formulate everything in terms of global temperatures. So the entire value of my functional for the entire mesh will be a sum of all nodal element contributions, and in each element contribution I calculate according to this equation, but I substitute this this equation there, which allows me to keep global temperature everywhere. So I still have this sum, but I can factor out those global temperature vectors and its transpose, and out of this sum and inside this sum I have these element conductivity matrices, and I have those matrix which describes how elements are connected. It's sometimes called localization matrix or incidence matrix, but it doesn't matter so much which name you use for it. In numerical analysis, usually you do not introduce this matrix directly as an object. It's more convenient to just make a loop and introduce rules how those matrices are constructed inside the loops in the code. That's what we will do. So the name is not so universally known of this matrix. But anyway, so that's full functional for the entire mesh. Sum over all elements, and E is number of elements. Local conductivity matrices, these incidence matrices and their transpose, and global vector of all nodal coordinates. So everything that is summed across all elements is in parentheses. Okay, I moved it here a little bit to make space for other things. So what does the variational principle now say? The variational principle says that any variation of the first variation of this functional for any text function delta t must be equal to 0. And if I use this principle with this equation, you will have to trust me a little bit here, because we did not deal a lot with calculus of variations. But keeping in mind analogy with differential formulation, you can easily see that it will be satisfied if this part without this multiplier 1 over 2, because it kind of go away because of this variational differentiation. It's how it goes away if you have in a differential equation you will have just something like t squared here, because it would be the same for scalar values or on the matrix level, and then this 1 over half will go away once you calculate the derivatives. You will have just temperature and this rest of this factor. This is what is here. And in the right hand side, because it must be 0, we have this what we have had here in parentheses. So we apply this variation to the temperature vectors, global nodal vectors here and here. And you need to be a little bit careful here, of course, but if you want to do that by yourself, but it's really nothing more complicated than you can easily see that from the definition that we gave earlier. And we end up with this type of equation. And what is that? It's nothing but a system of linear equations with respect to unknown nodal temperature values. So this factor in front of this, it's a matrix, of course, because those are matrices and matrix products. And this what's in parentheses here, we can call it K, global conductivity matrix, And what's in the right hand side, it's a column of values. You can see that. If you check, you will see that. And we'll call it F. And then it's equation of standard type, kt equals to F. And we know actually this K, because inside this K there are element connectivity matrices which we are able to calculate, and there are those matrices which described how the mesh is connected, how elements relate to each other, which we also somehow know. For any known mesh we can construct those matrices, so we can calculate that if we know the mesh. We know how the element works, and we know how the mesh is composed of those elements. Then we can calculate this global connectivity matrix. What's in the right hand side, we also can calculate that if we know applied heat flux. If it's nothing is applied, we just assume that it's 0 here. And shape functions we know, and again those matrices describe a connection between elements. So once we know the mesh and we know everything about the finite element, how it works, then we can solve this problem and find those values of nodal temperature. And that concludes the theoretical part of finite element methods. Of course, it's only for this. It's a little bit reduced for a simple example. I omitted a couple of things that you might have need in a more general case. But here is the idea. Any questions so far? Should we maybe make a break? How do you feel? I'm not, don't have any rigid restrictions in time today, so we can have a break and we can end a little bit later than previous time. It's not a problem for me, but either I can continue, it's also not a problem for me. So how do you feel?
Okay, we can continue.
Okay, no problem.
We'll take a break, it's okay. We can take 5 minutes.
So as you prefer. So if anybody, let's say so, if anybody wants a break, then we make it. Is there anybody who wants to make a small break? Okay, then let's continue. Why waste time? Okay, so now let's get. This was a little bit general. It was for the heat conduction problem for 2 dimensions, but still a little bit general. Let's do it for a particular mesh, and let's actually code it in MATLAB. Make a simple code that solves this problem. It's not something for which you already can guess a solution, so it's kind of interesting to solve it if we are able to solve it with finite element method. Of course, this type of problem you can also solve it probably analytically, but you can easily extend this problem to a little bit more complicated where analytical methods might not already work. Okay, so this is my mesh. I will use actually a more rough mesh with a lower number of elements, for example, to show you matrices, how they look like, but this is something how it in general may look like. We will be able to vary the dimension of elements in our code, and this is the element I will be using. The same rectangular element. I changed a little bit notations. I think there was some confusion with notations, some overlapping, so I changed it a little bit, and now it's dx. It's not a derivative, it's just my notation for this case. There are no more derivatives. All derivatives are inside those matrices already. So it's just my notation to emphasize that it's small dimension, x and y. And aspect ratio is still d. So nodal element vector of nodal temperatures consists of 4 components. Temperature here, 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 and here. global vector will consist of larger number of elements. So it's not its dimension is not number of elements, and it's not number of elements times 4, but it's number of nodes, because there are shared nodes. And this is the set of equation as we derived it just now. So let's start coding. Yeah, of course you don't need this clear all element. You can just use clear. Works a little bit faster, but well, actually it might work much faster than clear also. I'm not encouraging you to use this one particularly here. But first we need to introduce physical parameters. So I always like to keep parameters relating to my simulation somewhere in the beginning of my code. Not when they first arrive, but in the beginning it's easier then to find them and to control when you want to change something. So there is just one physical property in my problem, conductivity. Right? It will be somewhere inside those conductivity matrices. And something realistic would be, I put here 45 watt per meter per Kelvin. You can use something else, of course. But as previously, I encourage you to use some physically realistic values to be able to analyze the result, to use your intuition for analyzing the result. So it's a typical value for a steel, 45. Because there are elements with materials with much higher and much lower conductivity, but something realistic. We have some intuition about how steel types structures work. Then heat flux. Here you might not have some intuition about typical values. I put 500 as incoming heat flux and 300 as outcoming heat flux. This is my statement promise. Here the heat flux comes in. I don't know, it's heated by something, by some source of heat. It might be different. And there he loses heat according to some physical principle. Possible. So those are some kind of realistic heat fluxes. So it's not something that you necessarily need to be inside of a star to get this type of flux, and it also not something that it's negligible that you won't notice a difference in temperature. Some kind of realistic values you can meet something like that. If you approximate, for instance, radiation from the sun with heat flux, it's not actually a prescribed heat flux, but if you approximate it with it, then you might get something of that order. So it's just some realistic values. We don't need to make it equal to something concrete this time. Geometric parameters of my domain. So I used in this example, I used this horizontal size twice of the vertical size, but you can vary it. It must work with different dimensions if you code everything correctly, if we don't make any mistake. So this is about properties, physical statement of the problem. This is about geometry of our domain. Then about our mesh. This is something new. So we need to have a number of, it's convenient to introduce not size of element, but number of elements along each axis. And in this example, I want to use something very small, a very small number of elements. I mean, not small elements, large elements, and very small number of elements to make it easy to analyze matrices so that they are small. Then you will be able to increase that. So number of elements along vertical axis, number of elements along horizontal axis, and total number of elements, which is a product of those two. Okay, and this is number of nodes in this type of mesh. Yeah, this is a little bit less obvious, but still not very complicated. You can probably come up with this value on your own as well. Okay, this was introduction. Then more interesting stuff about how finite elements and how they are connected. So the finite element mesh itself, we will not be using any separate arrays to store kind of nodes, to store elements, but what we need as a minimum requirement is we will need coordinates of those nodes. Because everything is tied to those coordinates. You remember those coordinate transformation to local axis, it's tied to coordinates, and even if you don't do this transformation, you still need to know coordinates of nodes to be able to do your approximation. So I will be storing this matrix of x coordinates and matrix of y coordinates in this form. And those are dimensions of our elements. dx, dimension along horizontal axis, and dimension along vertical axis. So this is how this mesh looks like, the mesh that we introduced here. 3 and 4. So three elements in vertical and 4 elements in horizontal. This is how it looks like. And I put all the numbers here explicitly to explain you how it works. So let's introduce some numeration of elements. So both elements and vectors in our code, they will be a little bit of virtual. Yeah, so we keep them in mind, but we don't necessarily need to construct separated arrays containing them. You might do that, and you might find that useful in a more general case, but in this case we will just keep them in mind. So let's say we are using this numeration of elements: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 elements with this numeration of elements. And this numeration, the relation between numeration of elements and numeration of nodes, we will need to store it somehow. And this is the matrix I will be using for storing it. So, but first let's introduce numeration of nodes. Again, in our mind, the material representation of that will be this matrix. So the same principle from left to right, from bottom to top, I introduce continuous numeration of nodes. So overall we have 20 nodes and 12 elements. And those elements share some nodes according to this diagram. And I want to have a matrix that which describes which nodes belong to which element. So this is the matrix that I will construct. So first row is about first element, and it has nodes 1, 2, 7, and 6 belonging to it. The second row is about second element, so second element is described by nodes 2, 3, 8, 7. 2, 3, 8, 7. And I use everywhere the same rule of numeration of nodes within element, the same that I used previously: 1, 2, 3, 4. 1, 2, 3, 4. For element number 7, for instance, it would be 8, 9, 14, 13. Let's check. 8, 9, 14, 13. So this is the matrix that I want to have, and how I generate it. I used a little bit of a funny way to do it here. It's computationally not very effective because the size of your array changes on each loop iteration, which is generally not very good for with respect to computational efficiency of your code, but I think it's more intuitive in this way. And on each iteration of loop, so I make a loop according to a number of nodes in y direction, and inside it I have a loop over number nodes in number of nodes in x direction, and inside each loop I add inside both of those loops on each iteration I add this line for to my matrix. 1, 2, 3, 4, 4 elements, and plus this this term which represents a position with respect to y in vertical direction. So just one way I find it kind of funny and easy to understand how I describe this type of connectivity between nodes and elements. But of course you can make it computationally more efficient. If you need to run that code a number of times, it might make sense. But if you just it does not has anything to do with solving this system of equations. It's all in generating of our mesh. So just if you need to generate your mesh just once, it doesn't really matter how efficient is this part of the code. Okay. So now about boundary conditions. This might look a little bit complicated, but in the end it's also quite simple on the other hand. Okay, so the right hand side is this type of vector, right? Those matrices which are kind of implicitly in our connectivity between nodes and elements, and this is applied heat flux, and those are this is a matrix composed of shape functions. Here they are. But let's look, and in order to calculate the values which must come into the right hand side, I actually need to I actually need to calculate those integrals. Of course, in general case you would do that numerically, and for a general purpose code, you will have to write a general numerical procedure for that. But in our case, I want to make things as simple as possible to just solve this particular problem. Let's see what is in our case. In our case, we have heat flux. Let's start from this one on the left boundary. With respect to our mesh, this is the left boundary, right? So I will be have to specify something on related to those nodes. Sorry, it's a bit too fast. So this is one of the elements, imagine, on the left side of our domain, and I want to specify heat flux coming in here. So I will be interested in locations in this face of the element, this side. And this side is characterized by value in local coordinates xi equal to -1, left boundary. So whenever I put, whenever I'm looking at this boundary, I always put xi equal to -1. And those two shape functions, number 2 and number 3, they are immediately eliminated by this multiplier 1 plus xi. So on the left boundary, I always have n2 and n3 values 0 for any element actually. Okay, then this I also substitute this -2 here. Then it gives me 2, and 2 by 4 gives me 1/2. And so I calculate this integral for left boundary in local coordinates. It will be something like that, right? So zeros in the inside. The first term is integral. So I calculate integral of 1 minus eta. Okay, I didn't put it here, and it results in a linear term and quadratic term. And since I calculate integral from -1 to 1, limits are -1 and 1, then this quadratic term goes away because it gives the same value. So I only have values from this linear term which comes from integrating of this element. Okay, this element. So it's just I get just 2 as a result of integration. 2 over 2 gives me 1, and I just get q0, 0, 0, q0. This is a result of calculating this integral in local coordinates. In global coordinates, it changes a little bit, because we do not, even if it's still vertical in our global coordinates, we still need to introduce some correcting factor because of the scale. Because in local coordinates, length of the site is always 2. In global coordinates, it's something else. It's dy in our global coordinates. So if you imagine for simplicity, it doesn't really matter where you put the point of origin in this case, but if you imagine that it's in this corner, this is global coordinate, let's assume y equal to 0, then this will be y equal to dy, and you can express y through xi, so through eta, sorry, and eta is vertical local coordinate, and then you can calculate partial derivative for one with respect to another, and it will give you this value. Nothing difficult, just linear transformation. So if you want to have the value of this integral in global coordinates, even though the directions are the same, but still a scale factor, so we need to have this Jacobian matrix, which is this multiplier in this case. Determinant of Jacobian matrix, in this case, Jacobian matrix consists of just one element. Okay, actually there are 4 elements because they are even, but we are only interested in integral along this line, so we're only interested in this part of Jacobian matrix about transformation between a global y and local eta. So I just need to multiply it by dy over 2, these 2 elements. And this is the local part of this global vector related to certain elements on which the heat flux comes in this direction, heat flux of value q0. So I showed it here in a picture, and actually you could have guessed the right answer without even going into this trouble of calculating, thinking about shape functions and calculating integrals. Because if there is a heat flux q0 coming through this boundary, then heat flux is a heat energy per unit area, also per unit time, but per unit area, which in our two-dimensional approximation means per unit of this length. So the total action that is produced by the heat flux would be the value of heat flux multiplied by this length. And in our linear approximation, we just divide this value between 2 nodes. So it's just value of heat flux times this length and divide it between 2 nodes. It's as easy as that. And it's actually also a correct way to think how to compose this vector. It's not universal because if you used the quadratic approximation, you would have an additional node somewhere in between here. It's usually in the middle. And then it's not that obvious how to distribute this total heat flux between 3 nodes, considering that they are not equal. They are not equal in terms how they come into our interpolation. And that results in not equal values of heat flux. It's not just divided by 3, it's different in quadratic case. But in linear case, it's as simple as that. But we also made it formally. Okay, this is how we are going to fill this right-hand side. Okay, boundary conditions. So let's construct this right-hand side, essential part required to right-hand side. So this is my mesh. This is what the heat flux on the left boundary, how it looks like in terms of our finite element representation. So let's start with the natural boundary conditions, because we were talking about them right now. Natural boundary conditions are heat fluxes. So first I need to identify where those flux boundary conditions are applied. Physically, heat flux applies to a surface or to a face of an element. So I find it more convenient and more intuitive to associate these boundary conditions not with nodes but with elements. And that's not only me, but if you will be using some commercial finite element codes and you want to apply heat flux, it's usually that you apply it on faces of elements, like technically how it's shown. Because, of course, eventually there will be some contributions in the right-hand side which are related to each node. But it's more kind of physical to think about it associated with a face of element. So I will make this, I want to identify elements on which this left boundary condition from left side comes and this top boundary condition. So I will use some kind of flag arrays consisting of zeros and ones. So for left flag, zeros, number of elements, and 1, so which identifies which element from the global set of elements, which element should be associated with this left side boundary condition. And so I just put 1 in this array for these two elements, 1, 5, 9, and 0 for others. Okay. Okay, so I just make a loop with this step coming from here to here with this step number of elements in horizontal direction. So I got this direction, this, and I only put 1 in the first element of this. Oh, sorry, that's a little bit too fast. Then what's next? The same for the top boundary. So again, I make an array for the number of elements consisting of zeros by default, and then I put unity for these elements. Then I explicitly use the fact that left boundary is heat flux coming from left with the value Q0, and so I use this vector. This is precisely this vector that we formed here. Here it is. And for the top, well, for the top element, it will be the same except for the position. What will the position of non-zero elements? It's 1, 2, 3, 4. There is now our numeration within an element. And when I'm talking about top face, it will be nodes 3 and 4. Right, so similar how we obtain that for the heat flux coming from the left, we will have this type of vector. For the heat flux coming from top, we will have similar type of vector, but with 0 values for nodes 1 and 2, and non-zero values for nodes 3 and 4. So this is what I put here. So those elements which are subject to this heat flux on the top face, they are identified in this array by unit values, and for them I will be using this element level vector for the right hand side, and then I will compose all them together in the entire vector for the right hand side. But on the element level it looks like that. And final part here on this slide is I need to identify nodes for my non-zero, for my Dirichlet type boundary condition, or essential boundary conditions, where I have prescribed temperature. In this coil, I will be using temperature 0. I think I put it here. Yeah. So in our more general statement, it was some kind of any value of prescribed temperature, but for a little bit of simplicity in this finite element code, I will use 0 values. It makes things a little bit easier. We don't need to resort to one additional trick that you would need for non-zero boundary condition. It's not difficult, but it still takes time, and I just want to use as little number of tricks as possible to make as clear demonstration as possible. Of course, some problem becomes less general, but that's the price. Okay, so I just need number of those nodes to keep them somewhere where I will prescribe, in this case, 0 temperature. You remember that I will have to prescribe it explicitly. So it does not automatically come from variational statement of the problem. The variational statement, if I go a little bit here, okay, it's here. So this is the variational statement. So this set of equations, it comes from this first part of statement. This second requirement about essential boundary conditions, we will have to specify them explicitly. If there are non-zero boundary conditions, there is a trick how to modify this right-hand side to take them into account. But we will not be using this trick, so make things simpler, as I already said. So we will just specify this explicitly, impose them explicitly. Okay. Okay, so this is my set of nodes for which I want to have this boundary condition. Of course, I'm all the time in all those things I'm using this numeration how I defined it. So it's not for a random mesh. If you assume that numeration is according to some different law, all these things will change slightly. So, but it's just for this particular mesh type of mesh. It still we can vary number of dimensions. That freedom I want to keep, but I don't want to make it any different in other aspects. Okay, so not so more things are left for us to solve this problem. This conductivity matrix, and we start with local conductivity matrix. I copied it here. This is the one that I showed previously. And I just need to put it into MATLAB in any convenient way. So nothing, no trick here, just manually define this matrix in MATLAB. You need to have it. And for my particular mesh and for properties that I've defined, this is what I got. I hope you get the same. Otherwise, somebody of us made some mistakes, but we'll have to check for it. Okay. Okay, let me know when you are done with this. We will deal with the last interesting part probably in this problem is constructing global matrix out of these local matrices, knowing our mesh, how elements are connected. So does it work so far? Same results? Okay, I see some people are still looking at it. So I'll wait a minute more. I believe we still have some time. Yeah, there is not much left to compose global matrix and then to global vector of the right hand side and then just to solve it and visualize results. But we need to save some time to talk about the assignment also. But I suppose 15 minutes will be enough for the assignment discussion. Okay, I see that most of people did it. So now we need to combine it into the global matrix. So in analytical equations, we use this A incidence matrix. So this is kind of what we are going to do here. It's kind of the same, but we can do that in a loop. So what we need to do, we need to add up all elements of all local matrices together and position them in appropriate way in the global matrix. So what helps us to position is our matrix that I called unlock, our array, which is composed number of the row number is number of element, and the columns represent nodes which belong to that particular element. So I will be using this matrix to position elements of local matrices inside of the global matrix. And for that I need the outer loop is across all elements. And the two inner loops are from 1 to 4, which represent elements of kind of nodes represented to elements and elements of local matrices. And I will identify two indices IND01 and IND02 from using my unlock matrix. So for instance, for the outer, we are in the outer loop value number 1, value 1, first iteration of the outer loop, and we start from first iteration of the next loop, and so this first index is allocation of the value that is in our matrix unlock in positions 1 and 1. And 1, the first is number of element, the second is number of node in that unlock matrix. So in that case, this will be 1. The second value, when we go to the next iteration of this internal loop over jj, then it will be again first row, but second value, second node. So we were 1, 2, and then there were different values. Was it? I think it was 6, 7, 8 in our case, or 8, 9. It depends on number of elements, but you can look it up on previous slides. Okay, so this is the first. It's number of node, essentially, which is associated with element, this element, and in this position, which is in this position. Then we have another loop of a third variable kk, also from 1 to 2, and we have another index which is associated with the same element, number ii. This is the loop along on elements, but position different node, the node that is in position kk. And then we use this these two number of nodes to identify position in the global matrix. So the global matrix has dimensions of number of nodes by number of nodes. And we use these two values to identify a certain position in a global matrix. This is a global matrix, how it will look like when you do this set of loops. And then we assign it value from, we add to it, to previous value, the contribution from the local matrix. A local matrix is the same for all elements, right? So this first index, first variable of the outer loop has nothing to do here. So we use two different variables. So we assign certain contribution from from values according to those two indices, jj and kk, from the local matrix to that global, and we position it according to this numeration of nodes. So it's it may look a little bit not obvious, but it exactly matches this numerational rule that we introduced. If you introduced a different rule, you would have to make it maybe a little bit differently if you connected elements in different way. Not a little bit, just differently. So this is the for particular connection that we used. This is how we can combine. Matrices, and there is this sum because there are certain component of the global matrix may take contributions from different local matrices if it's associated with a node that is shared by elements. Most of the nodes are shared by elements except for the four corner nodes, and then this there will be contribution from all elements which have those nodes. This is what we do this in this line. We add a contribution to the previous value, we add contribution from the particular component of the local matrix associated with this particular element. This association is about how we position this, because it's here and here. Okay, so this was maybe a little bit not obvious part. You can check that it works correctly. And then we do approximately the same with right-hand side, but a little bit simpler because we have just one vector and along into just to position in appropriate way the vector of local contribution to this global right-hand side vector. So we are using only this one of the loops. We don't need both of them because it's one-dimensional. So we use this JJ. Yes, we use this JJ loop, and we use this IND01 value of this index associated with the element and the value of this variable in the first loop. And we find certain place in the global vector according. So this allows us to find place in global vector, nodal vector corresponding to the position of particular node of particular element. That's essentially the same as we did earlier. So this is how to construct this global vector out of these local vectors, where to put these values. So the same, this first index is totally fine, applicable for that. And I use if conditions, because it's only applicable to elements for which have this flag equal to 0 for the left hand side, and which have flag equal to 0 for top boundary condition. And then I add contribution from corresponding JJ value from this local vector, which we formed previously. Okay, so this is maybe the most important thing, how we combine matrices, local matrices, and to global. So this is kind of where the magic of the method goes, because we only need to define things for local for one element, and we will need to define, to explain somehow to the system how elements are connected, and then it will be able to solve for all elements. And this is exactly the way how we describe how those elements are connected in terms of stiffness matrix and this right-hand side of the equation. Okay, one easy thing that we also need to add, we need to apply essential boundary conditions. We impose them manually here. So we use this identification vector for nodes subject to this right boundary condition on the right side of our domain. And what we do two things. The most important thing is that we cross out corresponding rows and columns in the global stiffness matrix. Okay, it shifted a little bit here in my picture. Sorry for that. So this what is boxed with orange rectangles, it must be shifted by one row to the bottom. So this last line is what we do. And what we do is we cross out all values here and here for this. For instance, there is node number 5 associated with this boundary condition. It was here, so node number 5. So we cross out the 5th row of our matrix, global stiffness matrix, and 5th column of our matrix. And we put zeros everywhere there instead of original values, and we put unity at the intersection of this column and this row. Oh, it's here. So sorry again, it's moved. I didn't notice that when I was adjusting to this format, and it moved this picture with respect to those rectangles. Okay, and we do with everything. So it's easy to put zeros everywhere. So this is how we put zeros in rows and columns. So this is for the row. We put everything in the row associated with this number of nodes, and we put into the entire column associated with this node number from this array, and we put there zeros. And it's a little bit funny thing how we can put 1 at the intersection. Of course, there are different ways you can. I encourage you to come up with other. Oops, spoiler. To come up with other solutions when you see a better one, or just the one that you like more. It doesn't have to be necessarily more efficient, but this is one way how we can do that. This is by calculating indices in a global enumeration. So there is when there is an enumeration of rows and columns, there is a function that allows you to identify number of elements, like to use straight numbering of all elements in matrix. Like you have matrix 2 by 2, and it's element 1, 1, 1, 2, and you can number them 1, 2, 3, 4 all elements. This is and we can use this function to easily identify nodes that are at intersection of certain columns and certain rows. To identify diagonal terms, and we put there just a value 1. So this is how we put 1. It's here, and it's here. It's maybe not very much visible here, but it's here. It must be intersection. And we also do this modification with right-hand side, similar. We need to impose 0 temperature for those nodes. That's why we impose 0 values in the right-hand side in corresponding positions. So we have this matrix set of equations, matrix equation kt equals to f, and if we make for certain nodes, we make this matrix kind of diagonal. It's 0 in the row and in the column, and 1 at intersection. Then by multiplying this by the vector of unknown temperatures, we will get just temperature at that node. Everything else goes away in particular row of our result vector, and we make it equal to 0. We put 0 in the right hand side in the same place. Okay, and that's it. After that we can solve it. We can find T as a solution of the set of equation kt equal to f, and we can easily make some visualization to see how it looks like. So there is this contour f function in MATLAB, which you can use to visualize some value in a two-dimensional setting. So I'm using a set of coordinates, x coordinates of nodes and y coordinates of nodes to identify these settings, and I'm using this reshaped result matrix. I reshape this column of found nodal values into this type of matrix, having the same dimension, having dimensions matching to the dimensions of vectors of those coordinates. And then MATLAB is able to show me as this contour plot, so I can see a position, and colors identify value of temperature at specific position. The first picture I may put here is what I got for this 4x3 mesh, 4 elements in horizontal direction and 3 elements in vertical direction. So it's quite a rough mesh, and you can see that those either lines that correspond to a fixed value, to a certain value of temperature, and there are values put here by MATLAB, which I asked for here in this comment. and it's quite of not smooth shape. This is basically because it represents the idea that we have linear interpolation of temperature within each element. So you can see that those lines, there are literally linear lines of isotemperature, linear isotemperature lines, because of that linear interpolation. So you can see the consequence of that assumption that we assumed that within each element temperature varies linearly with respect to coordinates. We can clearly see that. Of course, that's maybe not very precise solution, and I would expect in a precise solution, accurate solution, those lines to be smooth ones. And if you run the same code for finer mesh, change n, x, and y variables, nothing else, you get the same solution. So it's the same problem, solution of the same problem, but more accurate one. And isolines now look quite smooth. There is still linear interpolation of temperature within each element, but elements are now quite small, and we may be satisfied with this level of accuracy that this mesh provides, at least judging from this picture. So that's basically it. If you're having any problems with it or don't understand how something works, please let me know. I will try to help you. Otherwise, I will explain the assignment, what I want you to do. So the easy way, I was thinking for a while about which assignment to give us, accounting for the fact that I already gave you first part of the assignment about this bar with finite difference method, and that part was about a slight modification of the code that we wrote together. So the easy way would be to make something similar modification here for this code, for this heat conduction problem. Like, for instance, to add heat generation inside the area. But I thought it might be more interesting and more educational for you to make on your own another finite element code, which is actually simpler than the one that we made, using the same ideas, even a simpler one, but for another problem, for exactly the same problem that we considered previously, this bar, but to solve it with finite elements. And it would be nice if you compared then solutions of your finite elements, solution obtained with finite element method and with the finite difference, and not only the solution but also the matrices, this matrix equation. In any of those methods, you end up with linear equations, ku equal f or kt equal f. Doesn't matter how you define, how to denote your unknowns. And do you end up with exactly the same equations or not? In finite difference scheme, central difference scheme, and this finite element method with linear interpolation between nodes. So this is the same problem. No new input related to physical statement of the problem, but you need to solve it with finite elements. I will give you some intermediate results as a structure to not get lost. So first we need to have variational formulation. We did not consider it for this problem, and again, I'm not going to prove it, but this is how the functional will look like. And by stating that variation of this functional equals to 0, you will obtain the same equations that you obtained earlier with the direct approach. So this is the functional, And note again the difference that we only have first derivative of the unknown function with respect to coordinate, whereas in strong formulation we had the second derivative. This right-hand side comes here. Sorry, I used different notations for the cross-sectional area. It's A here, but S here. Just pick one, whichever you like. Doesn't matter, of course. And this is integral along the line for the term corresponding to this body force boundary condition. But we also need this right-hand side boundary condition. And in this case, it's not essential, it's natural boundary condition because it's force. Forces in mechanical problems are natural boundary conditions. But since it's a very simple problem, it's only applied to one node. There is no distribution. There is no need to calculate any integrals. If it were a two-dimensional problem, there would be an integral over this side, of course. But since we are considered it as one-dimensional, so we just apply here value of the displacement at this node times this force. So this is what you kind of need, because you only need consequences that come out of it. Actually, you don't need to put this functional exactly. But if you want to derive everything on your own, then you should start from that functional. So the element that I suggest you to consider, you can pick something more complicated. If you feel strength and enthusiasm, you can try quadratic approximation here. The general flow will be the same, but you will have to work on those matrices on your own. So I don't ask for that, but if you feel like doing that, no problem, you can try and we can discuss the results, how it works. And okay, but what I suggest is linear interpolation, so just two nodes, xi minus 1 at one end, xi plus 1 at another end, and which corresponds to global coordinates varying from 0, for instance, to length of the element, value length of the element. So which gives me this transformation matrix consisting of just one component. This depending on transformation from which coordinate to which, it's either this value or reciprocal value. And in this case, I put the derivative of x global coordinate with respect to local coordinate. So the interpolation of a known displacement within each element in local coordinates using two shape functions, linear interpolation. So we have at the left end xi equals to minus 1. Oh, sorry, I think I left hand xi. Yeah, no, it's correct, right. So at the left end xi equals to minus 1, and we have 2 here, 2 over 2, just 1. And 0 here we have u equal to u1. Similarly on the right hand we have xi equal to 1. This terms goes away and we have just u0, u2, sorry. So those are two our shape functions, even simpler than in our heat conduction equation example, and still one scalar degree of freedom, just displacement along x. So it's really even more simple than what we considered. But I want you to work it a little bit with your hands on your own, even that it must be not complicated because you already have more complex example considered, implemented. But this way I hope you will get a better feeling of the method. And this matrix interpolation, matrix expression for the interpolation of displacements using nodal values will look like that. And we can calculate those derivatives of shape functions, this matrix of shape functions, with respect to xi, the only local variable that we have. It just gives us minus 1/2 and 1/2, simple matrix. But this is in local coordinates. Again, I mentioned I did not show that in very details. I just gave you result for this local connectivity matrix, but you eventually need to account for this transition from local coordinate to global coordinates when you are calculating that transition, when you are calculating local matrices. Also when you are calculating right-hand side, of course. So you can do that at this step when you can express this matrix of gradients in terms of global coordinates. It's of course the same matrix, but there is this multiplier because of this length transformation. So this comes into picture. Then we can calculate this local stiffness matrix. In that case, it was similar matrix, but in that case, it was related to conductivity. Here, it's related to stiffness, so it's natural to call it stiffness matrix this time. And I think it will look like that. And then you apply that into variational, into the equation for variation, and you apply variational principle. Again, there's 1/2 that goes away. That was here. And so does transpose of the global displacement vector. And this is the finite element equation that you eventually get. So this is global stiffness matrix, unknown vector of displacement at all nodes. Right-hand side has a contribution because of this body force, right? And there are shape functions, again those integrals. We discussed how to deal with them on the example of our heat conduction problem. What else? So the difference is that this time it's body force, but it's still kind of similar because in that case, boundary condition, there was integral over the face, that line, and now our entire body is just one line, so body force, in that case, it would be an integral over the surface. In this case, the body force integral over the line, so it looks similar to what we had for boundary conditions there, but this is body load, but in any case, they all end up in this right-hand side vector. And for this applied force, in this case, you don't need to sweat about how to apply this force. It's just additional force that applies to one node. In addition to contribution from body force, we have this nodal force. You can just put it as an addition to this very last node if you use numeration from left to right. Yep. And that's it. I hope that's enough for you to modify your heat conduction code into a code solving this problem.
The local stiffness matrix,
yep,
K, is in a global reference system.
Yes. In this case, yes, I already made this transition here. Right. But you please check. I think it's right, but I did not code it actually this matrix. So you please check. I want you to do that, and we will consider results. If something is wrong, you will immediately find out it because you already have solution for this problem with a finite difference method. That's why I think it's convenient to deal with a simple problem, but you already have another solution, and you will be able to identify any mistakes if you make them, or if you find that I made any mistake here, please, you're welcome to correct it. I believe there are none, but never know. Okay, so does it sound too easy or too difficult or difficult? Okay, well, the first part was easy about finding difference.
I wouldn't work on it right now, but
Okay, so it's all right. I did not formally give you this assignment. Okay, so I will stop recording now.